We are starting chapter 25 and we are going to talk about capacitance in this chapter. The section 1 is about capacitance. So first we will sketch a schematic diagram of a circuit with parallel plate capacitor, a battery, and an open or closed switch. And for a capacitor, we'll apply the relationship between the charge Q, the potential difference V, and capacitance C. So from now on, starting in this chapter, potential difference delta V becomes V, so we are dropping this delta, but whenever you see V, we are really talking about the potential difference unless otherwise is stated. Sometimes we will talk about point potential, like the point potential at point A or B or something, but usually in general this V represents the potential difference. So here, in general, let's try to understand what capacitor is, and we will also talk about how to calculate the capacitance. So two conductors or plates, and isolated electrically from each other and from their surroundings. You can see the negative Q, and on the other side we have positive Q. So you have these two, again, isolated electrically from each other and also from anything else, so it's an isolated system. But they're not sharing any charge because they're not in contact. So this forms a capacitor. It's very arbitrary shape. It doesn't have to be parallel plates, okay? Although I've been mentioning that a lot. Because of the geometry, things get easier, and we will talk about that, but it's one of the examples. So this is in general, this is a capacitance or a capacitor. And when the capacitor is charged, you can see the charged conductors here. The charges on the plates have the same magnitude but opposite sign. Okay, so we have a negative Q and a positive Q, and that what makes the capacitor. And you can see those lines with the arrows are the electric field, right? It looks kind of similar to the dipole, but we have some we can have different charge distributions. It doesn't have to be point charge. So we can have plates. We will talk about different cases as well, like spherical or cylindrical capacitors as well. So it does come in different shapes. So is there a simple relationship between the potential difference V and the charge Q on a capacitor? So from the experiments, what we see is if Q increases, the amount of charge increases, V also increases. And in general, they are related to each other with a constant C here. Okay, so as you can see here, if Q goes up, V goes up. And C is the constant. And C is the capacitance of the capacitor. So since it is kind of the constant here, it does not depend on the charge or the potential. We will talk about what it depends on. It's going to depend on its geometry. But this is the electrical equation. So I'm going to write later another one for geometrical equation. Electrical equation. And that is Q is equal to CV. And again, since you have three things in there, but what happens is when you increase the Q, V goes up. If you decrease Q, V goes down. Okay, so C does not get affected unless you're changing the geometry. So we will look into that equation later, but I want you to I want to plant that seed in your brain because that's going to be important, and that's usually the confusing part of this equation unless you realize that. Because when you change the Q on the left side, something on the right side should adapt to it, right? It could have been both of them, but it's not. And again, the capacitance is constant. So it doesn't, again, change with the charge. You can put more charge, but then the potential will increase. Capacitance will stay the same. The units for C, the capacitance, is farad. We use F, capital F for the unit, okay? And 1 farad is 1 coulomb per volt. Because it is, again, if you look at it, C is from the equation Q over V, right? Coulombs per volt. Again, if you forget about farads, you can at least say it's coulombs per volts. So one common application is a parallel plate capacitor, as I've been really mentioning this since the first time we saw about the electric field between the plates and such. So in the idealistic case, we won't have any electric field outside. If you look at the electric field lines on the right side, we won't have any electric field outside of the capacitor, parallel plate capacitor. But this is more realistic case shown here. So there are some edge effects here. You can see that there's some electric fields here. There's very small, weak electric field outside and on the edges. But again, when we think about the parallel plate capacitor, when we solve problems, we're going to look into an ideal case where we don't really have any of those surrounding electric fields. There's only electric field uniform, just like what you see in the middle here. It's very uniform, evenly spaced out, but when you go to the edges, you can see that it's a little separated more. So this is a realistic case, and again, that's not what we're gonna have. In our problems, we're gonna have uniform electric field between the plates. So what do we have here? We have two plates. Now I'm focused on the first left side of the schematic, and we have the area of the plate A, and the potential difference is V. Again, since we dropped that delta, it is still a potential difference, and we will be soon calling it voltage, but we will talk about potential. Just remember that it is a difference, okay? And the plate separation as shown here as D. And for this case, it says the bottom side of the plate has positive Q and the top side of the bottom plate has negative Q, because this is a conductor. Since it is conductor, so if you look at it close up, I'm going to just draw it from the side view. So if they are conductors, then you have positive Q only in the inner surface and the negative Q only in the, again, the inner surface. So there's no charge on the top surface of the top one, and there's no charge on the bottom surface of the bottom one. Okay, because these are conductors, the charges are free to move. They're gonna get as close as possible. They're gonna attract each other, and this is where the potential differences between these plates, because they have different charges. Again, to call this a capacitor, you need the same amount of Q, but this is positive Q, this is negative Q, and we say that this capacitor holds the charge Q. Okay, so now you know that the plates will have amount of Q, one is positive, the other is negative. And again, for an ideal case, we will say that electric field is zero outside. Okay, so again, these are ideal cases. And how can we find its capacitance? Okay, we're gonna talk about that. So we know that this electrical equation Q is equal to CV, but you also can write the C in using the geometry of it, like the area, the separation and such. And we will think about how to get that.